To solve the questions, I'll be explaining the concepts that we already talked about. So now we're given a decomposition reaction of that to give us nitrogen dioxide and the oxygen there. So if you look at our equation, this is what we have. That is our chemical reaction. And then if you look at our table, we have the time at start. You've been given the initial concentration of what? The only reactant, because this is a decomposition reaction. In a decomposition reaction, ladies and gentlemen, you have one reactant. So by decomposition, we mean it's going to be breaking down into its simpler forms. So that's why we only have a single reactant in such a case. So if you notice at start, all these other products are not available because it's a decomposition reaction. Then after 100 seconds, if the time is in seconds, we are told the concentration reduced, then these others increased. Then you continue looking at it as you go down there, you see what's happening. Now, the question is saying, calculate the average rate of reaction. So now, before we get to answer that, we need to understand what a rate is. Okay. So now the rates, ladies and gentlemen, you're looking at how fast. Whenever you're talking about the rate, you're looking at the time is involved here. How fast or how slow is a reaction happening? And you can look at it in two ways. You can either determine the rate in terms of the product or in terms of what? The reactants. In terms of the reactants, you get to determine the rate as the rate of change of what? How fast the reactants are being used up. So for example, this reaction, if I want, I can just determine the rate of the reaction by looking at how fast this reactant is being used. How fast is it reducing? That is one way of looking at the rate. The other way is looking at how fast the products are being produced. So those two ways you can determine the rate of what? A chemical reaction. Alright. So we are therefore going to say our rate is going to be, the first one is going to be the change. I can give it in terms of the change of what? The reactants over the change in time. Now remember, you need to divide also by what? The stoichiometric coefficient. Very important. You need to divide by the stoichiometric coefficient. In this case, you have a 2, right? You have a 2 as a stoichiometric coefficient of our reactant. So I'll put the 2 there. And then I'll add the negative. Now, why am I adding a negative? I'm adding a negative because I want my rate to be positive. Okay? That's why sometimes if you're not even sure, if you've forgotten, you're under stress in the exam, just don't put any sign. But if you find that after doing your calculations the answer is negative, go back and just add a sign to become positive. Okay? But very simple. For the reactants, we get to add a negative. Why? Because the initial concentration is what? The initial concentration is basically bigger than the final. Why? Because it is being used up with time. That's the way it is. So now we're going to substitute in our information. Okay. So negative. So the average rate, I will just look at the total time from 0 to the final point. So this is the final concentration of our reactants. 0.0061 minus the initial at start. 0.02. Change in time, 700 minus 0. Okay, we're good to go. Let's try to make our calculations there. We see what we're going to have. So 0.0061 minus 0.02 divided by 2 divided by 700 in scientific notation. What value are you getting? I'm getting 992 times 10 to the power negative 6. The units for our concentration is in molar, time seconds. So molar per second. That is the rate of. So you are saying that is how fast the reactant is being used up. In every second, we are losing about that much. And that much is like the rate at which the products are also being produced. Okay. Somebody else may be, okay, are we only supposed to use the reactants? Of course not. Let's try to use one of the products. We see what we're going to get as our answer. So in terms of our products, I can look at this one with 4. So the change in its concentration, I'll just go direct. So what is the final concentration? That. So 0.0278 minus the initial 0.0063. Or I can use a 0 at start, still fine. Then there is 4 there that I'm using a 4 because that's a stoichiometric coefficient. The change in time is 700 minus 0 as well. So 4 times 700, divide that into 0.0278. I'm getting 9.92 times 10 to the power negative 6. So irrespective of what I've used, whether the reactants or the product, I'm still getting the same answer. So it's all up to you, ladies and gentlemen, to choose what you want to use. So you've seen that I've not added a negative under this part. Okay. So now, for the sake of time, let me just guide you on how you get to answer the remaining question. Calculate the average rate of decomposition and average rate of formation. So they're just asking about the same thing here, except they're specifying the time. That's all. It's the same question, but they're specifying the time. Rate of decomposition, you're talking about the reactants. Rate of formation, you're talking about the product. Sorry, that's how you get to look at it. Now look at this. Now look at the specified time. They are saying between 300 and what? So this part. So they have asked for the rate of decomposition. So use this information together with the time and then also the stoichiometric coefficient to find the rate of decomposition. Then again use this other information for oxygen for you to find its rate of formation. Of course, taking note of the stoichiometric coefficient and also the time. You'll be able to answer that question. Okay. For the instantaneous rate at a given time, basically what we get to do most of the time is we get to look at you coming up with a table. You plot the table. You plot your coordinates. Okay. Let's assume you've plotted something like this. And then maybe your 200 is somewhere here. They ask for the rate of the instantaneous rate at that time. What you do is you need to draw a tangent against that time at that point. We do know that a tangent is a line that cuts a curve at a single point. So now, after you've come up with that tangent, you can get 2 coordinates. Maybe that coordinates and even that coordinates. So find its x and y, and then find the difference in terms of the gradients, in other terms. Yeah, you'll be able to determine the instantaneous rate at a given time. That's the easiest way. Okay. So this is the first part of the things that you need to know under chemical kinetics. Now let's move at the other part where we get to talk about how we get to determine the rate laws and the like. Before we get to look at the integrated laws, we can look at first of all the basic rate of laws, and how we get to approach them. So please, if you have a question, you are free to interrupt me. Do we have any question? Any question? Okay, it seems there are no questions. So look at this kind of a question. This will help us because this question usually comes a lot of times. Am I even talking to someone? I'm just alone here. So I confirm the network there. Maybe I'm not teaching.
So we can get you.
Okay, thank you. How do we get to answer this question? I'm sure we've been revising. We can't just say we've just been staying. No. How do you answer this question? Anyone? Anyone to guide us? First of all, have we understood the question? We have that given reaction there. The chemical equation is there. And then we've been given 3 different experiments on the same reactant with different concentrations. So experiment 1, the information has been given there as we can see. Okay. That is the concentration and that was the rate at that time. So it's like what they were doing is they conducted experiment 1 and then applied the principal battle from the first question, and then they determined the rate. Again conducted another experiment, again they determined the rate. So these experiments at different concentrations. And what have you noticed here? Where do we have a higher rate of the reaction? It's in the second experiment. Now if you look at the second experiment, you notice that it is the one that has got the highest what? Initial concentrations. This basically just reminds us of one thing that we need to know. Whenever we're talking about chemical kinetics, the rate at which a chemical reaction progresses in terms of how fast the reactants being used up and how fast the formation of the products. Like you get to look at what we call corrosion theory. Okay. Corrosion theory. This tells us to say that for chemical reaction to progress, ladies and gentlemen, particles of the reactants must do what? Must do what? Anyone, please, to remember this. It ends there.
With sufficient energy.
So it's what we call sufficient energy. And this sufficient energy, ladies and gentlemen, is called what?
Proper orientation.
With sufficient energy and proper orientation. Okay, thank you. So this is activation energy. That is a sufficient energy. It's a minimum energy required for a chemical reaction to just progress. Okay. So that is corrosion theory. So now, whenever you're trying to look at these factors that gets to affect the rate of a chemical reaction, let me just talk about these because they're also important. They can ask you about the temperature. They can ask you about the concentration. They can ask you about the pressure. They can ask you about what? Surface area. What else? Is there anything else that I've forgotten here? Of course, use of catalysts and whatnot. But I think these are the major things. Temperature, concentration, pressure, surface area. So temperature basically applies to all kinds of reactants. Whether they are in solution form, solid form, temperature applies. So an increase in temperature, ladies and gentlemen, increases kinetic energy. And the higher the kinetic energy, the more corrosions will occur. So we also have what we call kinetic theory. So kinetic theory focuses on the basic idea that when you increase the temperature of the particles, the kinetic energy does what? Increases. Okay. So when you increase the temperature, you are increasing the the number of collisions, because the particles will be moving with more energy. Okay, the particles will be moving more, so the chances of them colliding are higher in terms of the temperature. In terms of the concentration, when you increase the concentration of the particles, the probability of them colliding is also high. So it increases. The higher the concentration, the rate of what? The chemical reaction. Pressure applies to gases. So pressure, basically, we do know that it's inversely proportional to the volume. So the smaller the volume, the higher the what? The pressure. So in a smaller container, which has got a higher pressure, there are expected to be more collisions of gaseous reactants than like a one which is bigger. There are less collisions there. So the higher the pressure, the higher the rate of a chemical reaction for gaseous reactants. The surface area for the solids, what can you say there? Anyone who has got something to say? Do we have something to say? So surface area, if you talk about something that are reactants that are in that size, and then talk about the small ones, so which ones do you think have got a probability of reacting more? Is it the bigger ones or the smaller ones? Why do we expect the higher rate of reaction? Okay, smaller ones. So now which ones have got the higher surface area here? So surface area is bigger in smaller ones. Okay? If you look at a particle, a smaller one, it is able to interact with a lot of things like that. And like something that is bigger, because the particles that are inside are not going to interact with anything there. Okay. So the higher the surface area there, the higher the what? The rate of a chemical reaction. So I just wanted to make mention of those factors that are very important, and we can be basically examined on that. Okay. Now let's try to answer the question. So a rate, basically, you need to think of it as an equation that relates the constants, okay, against the products. So in this case, the products are, we have nitrogen oxide, and then we have H2. So now we basically don't know the powers to which we are supposed to be raised, the power x and y. So our goal is to find k and find the values of x and y in this question. Okay. So now we can use this very equation that I've come up with. It's not even hard to come up with this equation. If you've noticed what I've done, I've just like said the rate is equal to k, and then I've put my products there, or my reactants, sorry, and that's how I've come up with that equation, putting two unknown letters to denote the powers of the reactants. Okay, so I can start with the first experiment there and come up with an equation. So my rate is going to be equal to what is my k? I don't know. What is my nitrogen oxide there? What can you see? I have 0.01 raised to a certain power that I don't know, x, and then the other reactant is 0.01 as well, the power y. Then the rate has been given as 0.006. So where there is r there, I can remove it, and then I'll put 0.006. Okay, I can move the other one. So now it is advisable that as you get to look at the first one, as you try to find the first one, look at the one where any of the two reactants are constants. So in which experiment have you noticed that any of these two is kind of maintained in the certain reaction where the initial concentration is the same? Which experiment? In which experiment?
Second.
The second. What is meant?
Experiment 1 and 3.
So if I started with my second experiment, I'd have said no. It's a second. It's the first one and the third. Okay. So you can see that the initial concentration of that is the same even in the third experiment. So we can go for that. All right. So for my third experiment, my rate is 0.012. Then I have my K. My initial concentration is also the same there. And then for my Y, it is now 0.02. So we've come up with two equations, ladies and gentlemen, which is very, very simple to deal with. So my best advice is divide the smaller one into the bigger one. So you can see that the one that is down has got bigger values, right? We have a 0.02 there, we have 0.012 there. So I want to teach you the faster ways in which you can do your calculations in your exam. I don't have to basically write it in the way that you want it to be written. So, okay, let me write it. So 0.012 divided by 0.06. I'm just doing what it's like. I'm just dividing the one that is bigger by smaller values. And then we have K over K. Then we've noticed that this part is basically the same, right? So we're just going to divide and give us a 1. So we can even just remove it because it's just wasting our time. Not so. Is that okay? So you can just remove the K and the 0.01. That's why we wanted something where the initial and the final concentrations are the same. For the same reason, so that we can just remain with one variable. And then we can notice on the other part that we're dividing 0.02 by what? 0.01. Then all these are supposed to be raised to what power? So they're supposed to be raised to power y. Okay. And then we have a 2 there. I'm sure I can divide 6 into 12 two times. This side you also have a 2 to the power y. And then what will be the value of our y? What is the value of our y?
1.
Okay, 1. So we found the power now to one of our reactants. So remember the y was denoting which part? The hydrogen, not so. So we have the power 1 there. So now for the other one, we can just get anything that we can look at. Okay, any equation that we want. I'll go with the first one since I've already written it down there, and then I'll begin substituting. So what do we have? In fact, let me do this. We found that our value of y is equal to 1. How are we going to find the power of the other reactants? So there's no other part where the hydrogen is maintained. So we can just get any other two. Okay. So I can decide to go for, let me go for the same ones. So I'll maintain one and then I'll get the last one. So for our last one, or for a second one, sorry, I'll go for the second one. For the second one, our rate is 0.144. Then we have our K, and then we have 0.02, and then we have 0.03. I've just gotten the information from a second experiment. Now notice that we found our value of y to be equal to what? To be equal to 1. So I can just remove the y and put 1 there. Now our goal is to do what? Our goal is to find the value of x there. So you can clearly see that k is common, you can divide. And then which side do we have bigger values? The one down, right? So we'd be dividing the one on top by this. So we have 0.02 over 0.01. And this is supposed to be raised to the power at x. And then multiply against 0.03 divided by 0.01 the power 1. At that point, what we have 0.1144 divided by that. What do you expect to have? I'm getting a 24 equal to, then we have 2 to the power x multiplied by 3. So divide 24 by 3. What do you expect to have, ladies and gentlemen, there? That's like 8, not so. To the power x. And then 2 to the power 3. X is now equal to what?
Is it possible to have negative orders?
No, 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 no. It's not possible. Then you can. It's not possible. Why do you say so? So as I was emphasizing that basically divide this. Of course, if you also divide by the smaller ones, the bigger ones into the smaller ones, you'll still be able to get the reciprocals. But sometimes it confuses students, so it's better you just divide the bigger ones by the smaller ones. Okay. Is that okay? So now we found the powers of x and y. So x is equal to 3. And then our y is equal to 1. So our ratio
Yes.
is going to be k. Our first reactant is that. This one is the power 3. Then our hydrogen is the power 1. So this is our ratio. The overall order of the reaction is just adding 3 plus 1, which will give you what? 4. Which we don't even talk about in this case. We don't talk about such a reaction. We only talk about the firsts, or the zero firsts, first order and second order. Okay. But just for the sake of you knowing, in case where they ask for the overall order of the reaction after coming up with a ratio, you just add the powers. Okay, that is the overall order of the reaction. Now 3 is the reaction order in respect to this reactant. 1 is the reaction order in respect to the hydrogen. This question, ladies and gentlemen, if you're not careful, you're going to find it in your exam. Make sure you go through. It's going to be there. Okay. They like it a lot. I've seen it in the past papers. And then, how do we find the rate constant? So it's very easy to find the rate constant. All you get to do is make it a subject. And if you make it a subject, you're going to end up dividing the rate by nitrogen to the power 3, the hydrogen to the power 1, equal to k. Simple. You substitute. You can get any experiment of your choice and substitute in the information. Divide into the rate, you'll be able to get your value of k. Is that okay? Is that okay? We're too quiet.
Yes, sir.
Okay, so you can find the value of k. Let me just guide you how you find the units, just in case you've forgotten. So notice that in this case, our rates has been given to be molar minute, right? So I think it was supposed to be like molar per minute, something like that. And then our concentrations, of course, notice that they're always in what? In molar concentrations. Now, for this part, it is raised to the power 3, so even that would be the power 3, the power 1. And then you have something like molar per minute. Multiply against, this time that will give us molar to the power 4, equal to k. And then the k can cancel out on top, the m, sorry. And then you have molar to the power 3, multiplied by minute there. So these units can remain as they are, or you can take them on top, where you have something like this. To the negative 3 minutes negative 1. Those are the units of your K in this case. There's like a shortcut. Ruth and your shortcuts are there. Can you tell us your shortcut for finding the units? But for me, I used this from the retro. Yes. Capital letter M. The power what? Mm-hmm. Okay. Minutes in this. Okay, depends on the time that you're given in the question. Okay. So if you try to put the overall of the reaction, I said it was we had 3 plus 1, right? Which was 4. So which is I don't believe this can work. Okay, it has worked in this case. Yeah. So you've seen that the units are the same. So it's up to you to basically work with what the one that you feel can work. Yeah. So it's the same answer. Okay. Any questions? So I think for this morning we can just basically end here. Okay. We're ending here, but I'm giving you some questions to can look at. Please answer for me question 8 and 9. You can take a screenshot now. I'll need to see the solutions before 17 hours, before we continue with another lesson. I will do a bit of the integrated laws and then we'll look at chemical equilibrium. Okay. Answer for me these two questions. I'll be very happy. Yes, because there are people now when we say in the group, people don't share the solutions. So inbox me your solutions. What? Okay, so I've added the questions in the recording session because people who don't attend classes don't attempt the questions, so they should also attempt.